Hi, in this video we'll be working on an exact differential equation. So with an exact differential equation, we can figure out if it's exact. Well, first of all, if it's written in this general format. And what we have to do here, it involves a little bit of Calc 3. So we have to take the partial derivative in a sense of, so if we say that this function right here is m, and this function right here is n. So if we take the partial derivative of m with respect to y, and the partial derivative of n with respect to x, if these two are equal to each other, then we can use the exact process. So let's go ahead and do that. We have m of xy is equal to e to the x plus y. So we're going to take m of y, the partial derivative of m with respect to y. So basically what we do here is we treat anything without y as a constant. So the derivative of e to the x would just be 0. And then this would become 1. So looking at the other one, nx of y is equal to 2 plus x plus y e to the y. So looking right here, we'll take the partial derivative of this with respect to x. So same process, anything that does not have an x will simply be treated as a y, unless it's getting multiplied by it. So we'll take the derivative, this goes away, this right here becomes 1. This right here does not actually involve any x's, so it just becomes a constant. So right here we see that the partial derivative of the function m with respect to y is equal to the partial derivative of the function n with respect to x. So we can go ahead and do the exact process. So to do that, it's pretty simple. All we have to do is take the derivative of mxy dx, and essentially there's many different ways to go about this, but my particular way is just to add them up together at the end. So nxy with respect to dy, set that equal to 0. So we can go about doing this. The first one will be pretty easy. It's just e to the x plus y is equal to dx. This involves also, again, a little bit of Calc 3. You'll see right here that ignoring this right side, so right here we're going to take the integral of here, and we're only going to really focus on variables that have an x. Anything else just becomes a constant. So this is basically going to be e to the x, the integral of e to the x is e to the x, plus y times x, plus some function f of y. Can't have any x's there because it's the integral. Alright, so this is that left-hand side. This one's going to be a little bit more involved since we're going to have this guy right here to take care of, which will involve a little bit of integration by parts from Calc 2. So what we have here is the integral of 2 plus x plus y e to the y dy. Alright, that obviously becomes 2y. This becomes x times y. Now this side right here, I'm gonna move it over to this side. I'll actually use a different color, a lot of orange on this board. Okay, so we'll have y e to the y dy. So we know that from integration by parts, we can use this formula right here, where that's actually prime. So we can decide which one's which by this acronym right here, LIATE, which basically means logarithmic, inverse, algebraic, trigonometric, and exponential. So it's kind of like PEMDAS. So what this means is that if it's logarithmic, if there's a logarithmic function in here, this one will actually go first. So if it's inverse, and it'll go first. So in this case, the first one on our list is algebraic, which is just y. So we'll set that. So this will be the first one. U will always be the first one that gets set. So we have y, and then the other function will simply be put on the bottom right here, right? So e to the y. So the derivative of u in this case would be 1. the integral of v prime is just e to the y. All right. So this is the formula that we'll be using, u prime b du. Okay. So plugging in stuff, we'll get y e to the y minus the integral of u prime 1, right? So 1 times v, which is just e to the y dy. I'll take that away for confusion. Okay, so that goes away. And we know that this is just going to be y e to the y minus e to the y plus some function f of x, right? We can think of that as a constant. I'm not going to distribute the negative because essentially it's just a constant. The sign doesn't really matter. So plugging this in to here, ye, right, because this is just the integral. So right here what we did is on that side. So y e to the y minus e to the y plus f of x. So this is the function that we're looking for, f of xy, right? We'll go ahead and add these up together. If there's any repetitions, they do not get added together. Say if there was another e to the x on this side, right? So we have plus e to the x that stemmed from this integral, right? So there's an e to the x in this integral and an e to the x in this integral. It would not be written as 2e to the x. It just repeats, so just leave it like that. But in our case, there's no repetition, as we will see. So we have f of x, y. Actually, I'll just leave it as f of x, because it is defined implicitly. So we have e to the x, right? There's no more e to the x's, no more common. So then we're going to get e minus e to the y, right? And then I have here xy and xy, so that's going to be plus 2xy, right? And then right here I'll have plus 2y, and then I'm left simply with a plus ye to the y. All right, and the initial, this is an initial value problem, so let me get the initial condition, which is, oh, it's actually not an initial condition. Oh, it is an initial condition, yes. Okay, so y of 0 is equal to 1, right? So again, this is our general solution. So in order to get to our particular solution, just plug in the initial condition. We'll get that in the end, actually this is going to be equal to some constant. There you go, now it makes more sense. Okay, so we're going to get, in x we put 0, so e to the 0 minus, and then in y's we put 1. E plus 0 plus 2 plus, and then we have e. Double check. Yes. Okay. So simplifying out, this is just going to be equal to 1. And then these e's cancel out. Plus 2. So c is equal to 3. So just erasing that c, we get 3. And this right here is our particular solution to this problem.